Wow, it's great to see such a great turnout for this topic. Thank you for coming. So my name is Dejan. I'm an engineer at Red Hat.
And hi, my name is Ted Ross. I'm also with engineering in the middleware group at Red Hat.
Yeah. So today we want to talk a little bit about edge computing, but try to put a little bit a different angle on the topic. So usually when we talk about edge computing in general, and especially in the Kubernetes environment, people usually talk about infrastructure and platform and everything like that. But today we want to focus more on a developer experience and developer angle to the edge computing. So just a quick intro to the topic itself. So we don't want to waste too much time on it. So to me, edge is an extension of the cloud. So it's not something that depending on who you talk to, there are a lot of different type of edges out there. So we can start with the device edge and node edge that are in the end user and premise space. And depending on how you look at it, it can be a really a constrained node and environment, or it can be a really small cluster. And then you can go into the provider edge space when you have a typical service providers like telcos and ISPs trying to put their resources to the work and trying to provide mini data centers and again a more powerful clusters as an edge computing sites, right? But depending on which of these type of edges we're talking about, there are different things that we need to consider. For example, in the provider edge environment, network bandwidth and network latency usually is not a problem. While the more you go to the left of this diagram, you will see that resources becoming more constrained in the compute sense, but also in the network sense. So the network bandwidth become more expensive and less reliable. And that's some of the things that we need to think about when we try to develop services for the edge. Also, this diagram trying to put a little bit more sense into why we want to do edge computing and what is the cost in trying to do that. And like with everything in engineering, there's the trade-offs always, right? So the closer we put our compute resources to the edge, we get some benefits of less relying on the bandwidth, increasing the latency of data processing, and achieving greater resiliency and of our edge sites, right? But we lose economies of the scale, which is one of the main reasons why we do cloud computing in the first place, right? So the management overhead and the cost of the control plane is becoming more expensive the more we go to the edge. So having all that, when we think about edge computing, there are basically three main category of challenges there. First one is infrastructure challenge. So how we actually physically put our compute nodes on the edge sites, right? So it's not secure data centers. We don't have a lot of experienced IT personnel to do that. And other level is a control plane challenges. So once we have this compute infrastructure there, how we actually put our workloads on those edge nodes, right? And finally, once our services are running on the edge sites and on the cloud, the question is you know, how we develop applications for this distributed environment, how these services communicate with the cloud and with each other. And today in this talk, we want to focus mostly on the third part of these challenges. So for all applications and services running on the edge, there are two main challenges remaining. As you said, resources are always going to be a problem, because once we're on the edge, we lose the auto-scaling, the magic of our centralized clouds, meaning that we can't easily add more nodes and more computing power as we need it, right? So we need to be careful of how we prioritize our services and how we do a capacity planning for these sites. And as I already told, so network is usually limited, usually expensive, and we need to make sure that the services are being able to communicate with each other. So when you take all this in consideration, there are a couple of things that is always that we need to take care of when we're thinking about deploying our microservices on the edge. So first is, sorry about that, deployment itself. Other is the node resources. Third is how we're going to do the communication, and finally the security is a big concern, because in some of these use cases the edge sites are running outside of the physically secured data centers. So usually on the infrastructure that's unattended. So we need to have a tools as well that will provide us a proper guarantees that we are running actually the services that we think we want to run, right? So having all this in mind, we need to figure out how we're gonna use existing toolkit that we have in the cloud native space to actually do this job. And there's a lot of hype in edge computing these days, and everything is labeled as edge. But for me, something to be called edge computing needs to be extended from the cloud native technologies, right? And with that, we can use most of the tools and best practices that we use today, and then apply some special considerations in a couple of main benefits to do that successfully. So first thing that comes to mind is how we solve the deployment problem, and that's where GitOps best practices can play the role, right? First of all, we want to have our environments to be operated by people that are not highly trained IT specialists, right? So it needs to be as simple as possible, and these edge sites are usually running in the private networks. So we don't have basically tools to dial in those environments and do the configuring we want, like we could do in the publicly hosted clusters, right? And I think that's where GitOps practices we have today play a good role. So we can define our configuration and our whole developer environment and treat it as a code. So all our YAML definitions and all our secrets should be hosted in the Git, and by using that we can use the same development workflow by doing the pull request branching and CI/CD testing to manage this configuration. Once we have that, we can have some kind of the operator running on the edge site, basically pulling the changes from the Git and applying those environment changes in the cluster. as I said, a couple of things that makes this even more interesting in the edge sites is that, simplicity for the managing the edge sites in this way, and ability to do it from the site and not connecting without having the external access to those edge sites. What we have in this toolkit today, I think should work pretty well in most of the use cases. So the Flux is pretty popular GitOps operator, and we can use the tools that we use for other stuff like Helm and Fabricate to actually create those environment configurations. And once we want to store some secrets in the Git, I think the sealed secrets project could be a good fit to keep encrypted versions of the secrets in the repositories, which can be encrypted only by the proper operator on the edge side. So the other thing is how we're going to deal with resource constraints. So we want to make sure that our services are as small as possible and using the resources and CPU and memory as less as possible. I know this is not a typical Java crowd, but if we want to be successful in developing Edge, we need to have a solution for all the languages and attract developers for all the environments. So one of these examples is the Quarkus project, which provides a cloud native Java using Graal VM to basically compile Java applications to native applications, which drastically reduces the memory footprint and the startup time of these microservices. And it's good in a cloud native way, but as I said, like some things are even more emphasized for the edge environments because we don't have unlimited resources there. And beyond that, even if our resources are small and efficient, there's always a problem of not having enough of them on the edge. And that's where Kubernetes provides us with its prioritization toolkit, which allows us to define different classes of citizens, different classes of services running on the edge. And depending on how we configure some of these settings, some of the services will have higher priority and will not be evicted in case of resources becoming scarce, right? And I'll hand over to Ted to talk a little bit about networking. And
thank you. Thanks, Dejan. I'm going to actually switch gears a little bit and take a deeper dive into the question of networking and cluster interconnect. And just a quick word about the state of TCP/IP and the internet and the way that it serves us. As you know, the way that the internet is constructed, and the way that it is able to scale so large is that it's divided into public subnetworks and private subnetworks, and that's enabled by network address translation and NAT routers. So there are millions upon hundreds of millions of private clouds, private networks, of which they may be sharing many of the same addresses. And the orientation of this network is vertical, where you have server clients in those private networks and big expensive servers up in the public network. So the internet is built for a client-server world. But the thing that we're going into right now, the more modern development techniques that we've been talking about, hybrid cloud, microservices architecture, serverless, et cetera, is distinctly not client-server. We want to be able to put services anywhere, and we'd like them to be able to talk to each other. So, in this illustration, I've got two hosts in private subnetworks, both of which share the address 10.1.0.5. Clearly, these two hosts cannot talk to each other or address each other directly. They can interact through chat or maybe Google Docs or some such thing, but it's going to be, the software that enables that is actually designed in such a way that it's talking using some sort of protocol going through some public service. So this is exacerbated in the world of edge computing where we may have lots of small private subnets. And we really want to have a way of giving developers the ability to interact more directly through that. So with that little piece of background, we're going to introduce an idea that we're working on. This is a new thing that we are working on in an open source project called Scupper.io. And it's the virtual application network, where we're going to talk about services. So here I've got a set of services, and I've drawn one client, but of course there could be many. And instead of dealing with IP addresses, because we can't address those services using IP, we want to address them in a more application-specific way. So in this case, in this particular network, I've introduced a router into each of my locations. Think of this as networks or clouds or Kubernetes clusters that may be in different locations. And TCP/IP is used for what it's good for, which is the connectivity, the vertical connectivity, getting everything hooked together. But the application network allows me to talk about these services with a name called service, and then allowing me then to distribute my application traffic. If that service is an Anycast load balance address, then the load from the client load can then be spread over all these servers, regardless of where they are in their location. So some of the implications, and I'll do this quickly because time is of the essence. We've got some security implications. When you have a network where you're addressing things at that level, where access control is expressed in terms of the application or the business logic. I'll talk about it as the business resolution. The network itself is locked down. The connections between those routers are mutual TLS, and best practice, as we recommend, is actually using a dedicated certificate authority. So those are very locked down, and the cross-cluster applications, so if I've got a service in one cluster being accessed by a client in a different cluster, there's no exposure. That service is not exposed using Kubernetes networking or OpenShift routes or anything of the like. It's tunneled. So the public exposure is then limited only to the ingresses that you create in your application for getting things in from the outside world. There's also the notion of a trusted or an untrusted edge, where we can actually say that router in the edge, well, we don't really trust it, so we're going to apply our policy actually where the router hooks into the network, the edge hooks to the network. And that actually simplifies the development of the code on that edge itself, because it's being enforced at a higher level. And then from a management and monitoring, the metrics are also collected at that same resolution. So you have counters on the actual services and the actual business objects and the processes that you are running. And I will point you to the project where, I've actually skimmed over things at a very high level here, but you can learn more by looking at the project. And this is where we are doing this work. This is a new project. It's emerging technology. The emphasis here is to make it easy to set up networks. We want to be able to set up networks not requiring any advanced networking, no software-defined networking, no VPNs or tunnels or IPsec, firewall rules. A developer need not have elevated or admin privileges or cluster access, and there's no issue with overlapping address space. So it's very applicable to the edge computing world. There's no single point of failure. It uses a redundant topology. And it supports multiple protocols for your applications, including gRPC, HTTP, TCP, messaging protocols, et cetera. I'll talk about a couple of use cases where this is useful. And here's a case where I've got an edge site connecting a number of devices through some technology, but those devices are either being controlled or they're providing data for some services. And those services can be in the public cloud, or they can be at the edge site, or they can be both. And what this actually allows is for situations where the edge site and the public cloud become disconnected. The devices can then still operate in their local area disconnected until there's a reconnection, and then we can reconcile with the public cloud. And this is a typical edge case, particularly if you have like satellites going over buoys in the oceans and things like that, where you are disconnected for some time. Edge-to-edge integration. Here's a case where I've got 4 different cloud locations. 2 of them are in private edges and 2 of them are in public clouds, and I have a redundant topology set up. In this case, in this picture, I've actually got arrowheads. The arrowheads are only significant in the direction of the establishment of connectivity. So the edges connect upward through their firewalls to the public cloud because it can do that. We can't connect backwards without doing special tunneling. But once the connections are established, the arrowheads are no longer significant, and traffic can flow in both directions over these lines, so that the services in these edge sites can then talk to each other seamlessly. Here's basically the same picture, but in this case, I've got clients in both edge sites using their local services. So here's a case where we're enforcing or using locality. Clients use their local services where possible, but if those services either go down or they become backed up and the latency goes up, then this network can spill over to the services in the public cloud, and it can even spill over to the services in other edge sites. And also in a more messaging-oriented use case where we've got a network where we absolutely must be able to produce. We've got a very high degree of requirement for availability for producing messages. And here's where you can actually have multiple sites, you can have routers and multiple brokers running, where the probability of having one up that can accept your deliveries is increased. So I've left a little bit of time, and we're going to do a demonstration. And I'm going to actually show you a picture of this demo before we start it. So this is just a quick picture of what it is that we're going to be attempting live here. We've got a core network that's actually AWS. It's running on the US West availability zone. The one on the right is a private cloud. It's actually running on a server in Raleigh-Durham someplace. And the one on the left is going to be on my laptop. So let's see how this goes. What I have here is a couple of CLIs and a console. And the headquarters is depicted up here, and the Raleigh-Durham one is depicted down here. These are already connected. But on my laptop, I have basically what amounts to an empty namespace right now. There's just nothing in here. So I'm going to use the scupper tool. I'm just going to say scupper init, and this says enable scupper for my namespace. And when I created the one in the public cloud, I actually generated a connection token, and I have made that connection token available to this laptop by whatever means is necessary. They both happen to have been run from the same one, so it's in my file system. So now if I do a scupper connect, it was US West, and that's the connection token. Token is a little YAML file that contains the information needed to set up this connection to the network. So this, if it all works well, is going to connect my namespace. It's going to introduce a router, and there it is, on my laptop's namespace, and it's going to make a connection to this is the picture that we showed you just a moment ago. So let me show you some of the connectivity here, just to illustrate what's going on here. So if I say cube control show services, get services. So there's just a couple of services that were created for the purpose of doing this networking. Now I've got a tunnel, an SSH tunnel, over to my RDU server, and I can also do the same thing here. Keep control, get services. But I have a service over here that's my Edge service. This is part of my application. Now, I didn't even mention this. I should have probably said this, but we're showing what is like a electric car charging station, where these stations are all edge locations. They have a certain amount of resources, and they're being managed by a headquarters. So this Edge service is the one that is providing this charging service. Now, if I were to do let me see if I've got it right here. So I'm going to do a curl. It's just a straight up HTTP REST type service. And since I'm on that same cluster, I'm cheating here in that I'm not using an ingress or a route, but I've got the address available. And this is the Edge service address. It's on port 8080. And I'm going to ask it, what's the status of my slots? Well, I've got 10 slots, and they're all free right now. So I can then go in here and post. Now, I'm not doing anything fancy here. This is just one cluster with a little simple web service that's running. And I'm going to ask it to reserve slot 4, and see if I typed it right. So slot 4 is now reserved for use, and this can be done remotely because maybe the station I'm at right now is all filled and I want to reserve something nearby. So back here on my laptop, I would like to be able to access that service. But it's not running here. It's running in Raleigh-Durham on some remote thing, remote network that I don't have access to. So what I'm going to do over here is I am going to annotate. If I'm lucky, I've got it in my... Okay, so I'm going to do a kube control annotate. I'm going to annotate that service with a scupper-specific annotation. I'm going to just tell it I want to proxy that via HTTP. Now, when I come back to my laptop and I have a look at the services, I have a service of the same name, Edge Service RDU0. This is the same, there's no pod here running. The pod is running over on RDU, but now I have a proxy service that is located elsewhere in the network that allows me to have access to it. And this is what the application layer networking is doing, so that the address of this service is actually Edge Service RDU0. And if I curl to that, let's see if I can type coherently. Get HTTP, and I'll grab that address. And I'll give it the right port, and I'll say Did I mess it up? All right, it didn't work. All right, so let me see if I can get my, now you'll notice also in this, this is actually the router console, and it has a few little visualizations for traffic, so it actually is showing that flow of that traffic when it occurs. So since I'm running this thing out of the laptop, and it's being serviced over RDU. This is actually showing that, well, the network, since there's no connection between the two, it has to actually go via our public headquarters to get there. I think, given the time situation, I will let you close us up.
Yeah. So, we had just a little bit of time just to scratch the surface of all this discussion. But if you want to try to start developing edge applications, it's not all about infrastructure. It's not all about platform. We need to start solving problems for developers and how we're going to address those challenges. So we try to provide some of the guidance for three aspects. So how we're going to deploy those microservices to the edge. So use some of the GitOps existing tools. Try always to make sure that your service sizes are as small as possible for the edge environment. So try to find the appropriate framework for the language you're using, and try to use the existing toolkit for prioritization that Kubernetes gives us, and finally, try to think a lot about the networking considerations. How we're going to connect those services, and how we're going to provide like a uniform experience for developing applications in the edge. So yeah, we don't have much more time. So there's a Kubernetes IoT and Edge working group that discuss all the things related to these kind of topics. So if you're interested into it, here's the link that you can see to join it. And on Thursday, the working group have a more IoT-oriented session on how we can use more specialized protocols and in the context of Kubernetes. So now we have a couple of minutes for questions. So.
This might be not the best question, but I thought Istio was trying to solve similar challenges. What is this doing that Istio cannot?
If I'd taken bets on what the first question would be, that's the one we always get. So how does this relate to Istio? So Istio is a service mesh, and it's really about the connection of observing and instrumenting the connection between HTTP-based services. And there's some overlap, obviously, between what we're doing and what they're doing. Our focus is really, it's a different approach to multi-cluster communication. And our focus right now is really on just the communication aspect, because we believe that there's a lot of difficulty involved in non-star, non-full mesh types of topologies when you're talking about multi-cluster, particularly when there are private networks involved. So there is overlap, and obviously Red Hat is very involved in Istio, so we have people that are doing both, but we're exploring a new a different approach to providing this kind of connectivity.
I have a follow-up question to what the previous question was. It's not about Istio, but there is a network mesh, which also has at least some of the use cases similar, where you can connect, I think they use OVS over that. You can have any kind of connectivity within private network or outbound or whatever. So just a question is, do you use that? Do you plan to use that? Or how do you relate to that?
Let me make sure I understand the question. You're talking about, so there are actually there are quite a few projects underway that are trying to solve the cloud connectivity issue. As far as I know, almost all of them are dealing with the problem at layer 3, at the IP address level. And so we're trying to do it at layer 7. Because we actually believe, especially when you get into the edge spaces, that layer 3 is going to give you problems. Because when you've got two identical subnets and you're trying to make them work together, you're going to do a lot of very unnatural things with TCP/IP to make that work. So we are heading in a different direction with that. I'm sorry, this is not layered on top of one of those. There's no IPsec, there's no VPN, there's no anything underneath this. This is a different approach.
From the demo, it's completely in the user space, on the application space. So there was no any special network configuration to connect this laptop to the clusters running in the under some VPN. Yeah.
It can do things that some of the other approaches can't do, like load balancing across different locations and multicasting across different locations and such.
Is the dashboard collecting latency information or latency metrics between the edge clouds, between the services of edge clouds?
You said is the network collecting latency information?
The dashboard that you showed during the demo.
No. But when it's doing, if it's doing load balancing, it's actually using latency-related information. It actually knows what the backlog is for every individual server, and it can pick the server with the lowest backlog. The aim is to make even, we want to have a low variance of latency across the entire network, and that's the way it's designed. But it's not specifically measuring latency to do that.
You said you are not using any tunneling or anything like that, but I am wondering, even for layer 7 traffic to flow, something has to be there at the lowest level, right? At the layer 2 or layer 3 level. So what is the magic happening? For your laptop to connect to your this one, how is it connected?
Yep, it's using TCP/IP to do the vertical, to a router connection. But as long as there is a total connection, a path across the network, what's actually happening is these routers are doing link state routing at the application level. So it actually is using an OSPF-like protocol to determine what the topology is and what the best paths are, so you can have redundancy. It'll react to changes and such.
The laptop which is connected to the router in this arena is doing the OSPF to the. That's how you get the connection.
There were 3 routers in the demo. Each one is a link state router.
But it's important to say that they're not IP routers. They're messaging routers on right. The layer 7. Yeah.
Right. Oh. It's not OSPF, but it works just like OSPF.
Okay. So this laptop itself instantiated a router for that scenario to connect to the other.
I'm sorry. Say that one more time.
The setup that you set up on the laptop, right? The Kubernetes one. It had an instance of a router that talks layer 3 to the outside world?
The router is a container we deployed on the Kubernetes cluster that's running on the laptop.
Okay, so every edge cluster should have a layer 3 router spun up as a container. That's what you're saying.
You can try this yourself if you like.
Oh, okay.
So we'll try to put this demo. It's not ready yet to be reproducible, but the goal is to as a part of the Scupper project. You can take a look at a lot of different examples there, but even this example for the edge computing will be there soon to test it out.
At what stage this project is enter the CNCF?
Currently not. Yeah.
This is not a CNCF project.
It's a very new. So
it's a very new project.
Yeah.
All right. Thank you all for coming.
Thank you.
Very good audience.